So hello everyone, in this particular video we are going to see the biasing of MOSFET. So I hope now you all know that what is biasing and why biasing of any transistor is required. Okay, so before coming to this particular part I would like to tell you that why biasing is needed. Okay, so this is the plot between the output voltage versus the output current. As you can see, this is the output current and this is the output voltage, right? Output voltage. Let me just decrease the thickness of the pen. Okay, just a second. All right, so now what I will do, I will just draw a line joining these 2 points. Which 2 points? These 2 points. See over here, this is the maximum current and this is the maximum voltage, right? Okay, so now when this particular line joins to this particular curve, as you can see, and basically we had seen this particular curve through our post. So it's my request to you all guys, those who don't know about how this particular curve has came. So it's my request to you all guys, please do visit my post. The link of that particular post I will embed in the description section, right? So just read that particular post and you will get to know all the concepts in great depth. Okay, so this is the point which of which I'm talking about. So this is known as Q point. This is known as Q point, and this Q point should be such that your IDSQ, that means the uh, this particular current over here, that means this one, this particular current, right? It should be such that it should be half of the maximum current, maximum output current, right? And your VDSQ, that means this particular voltage, this one, okay, it should be, no, sorry, it should be VDSQ. Yeah, it's VDSQ, it should be half of the maximum voltage, I mean the maximum output voltage. So these are the 2 points you should consider whenever you are uh, plotting an output whenever you are dealing with the output characteristics, right? Output characteristics of transistor. All right, so I hope you understood up till here. So let me just draw one dotted line and then we will conclude certain things out of it. So maybe let's suppose if I'm considering this particular point and this one somewhere over here, yeah, something like this, and let me just take this projection downwards somewhere over here, this Q point over here and this one over here. Okay, fine, and let me also draw these projections over here, and let me just extend this projection till here and this one till here. All right, so let's suppose if you are giving an input voltage to this MOSFET. Okay, let's suppose if you are giving one input AC supply, okay, or AC voltage, which is obviously its magnitude and its amplitude is pretty less, and that's why you had basically designed this particular circuit. And further lots of stuff is being used like capacitor and all, and then frequency will also play an important role over there. But that is not important as of now. We just need to analyze this particular circuit, right? And we at the output we require amplified form of this particular circuit, right? I'll just draw it properly. Yeah, so this is how we require, or basically this is how an amplified form of this particular uh, signal will look like, right? So as you can see, let's suppose this is the input waveform you are feeding to the MOSFET, right? And at the output side, obviously you are getting the amplified form of this particular input signal, right? So basically you are getting amplified form of this particular input signal. Okay, so now if you could see very clearly, as your Q point is exactly at the center, right? So that's why you are getting the amplified form. But now let's suppose if your Q point is lying somewhere over here, maybe somewhere over here. So obviously due to this particular this point, that means see over here this was your Q point and then it shifted to the right side, right? So that's why as your Q point shifted to the right side, just a second, so this particular signal which you are seeing at the output, this particular signal will also shift somewhere over here. Just a second, let me just draw a rough projections. Oh sorry, let me just draw one rough projections over here, indicating that your Q point might have shifted somewhere over here, right? But that is not big deal, that is not an issue. What is an issue is this. See over here, this particular part, it is getting clipped, right? This particular part is getting clipped. Okay, so we understood that, you know, the Q point should be exactly at the center, it should not move towards the right side. Okay, so this is the very first conclusion we had drawn. I'll erase this all of these things once again, and then we'll also draw the second conclusion by looking at this particular characteristic, right? Now let's suppose if our Q point is going somewhere over here. Let's suppose if this is the Q point I'm talking about. Let me use yellow color, because since we had used yellow color for the Q point, so I'll prefer using it only, right? And due to this particular shifting of the Q point to the left side, this particular signal which you are getting at the output, it may also shift. Okay, so let's suppose if it is shifting somewhere over here. Okay, something like this, and let me just uh, draw it little roughly. Yeah, so yeah, something like this. I know it is not uh, I had not drawn it properly, but still what is important is to see this. As soon as it shifted little leftward, so this part got clipped. Okay, so basically we drew two conclusion out of it. That is, our Q point should not shift to the right side, and nor it should shift to the left side. It should be exactly at the center, so that we will get a proper magnified form of the signal, right? So this is what we had seen till now. So let me just erase these particular things. Yeah, so this is what we had seen, and that's why uh, I had intentionally written over here that our Q point should be such that it should be exactly half of the output current, and our VDSQ, that means the this particular uh, parameter, it should be exactly half of the output voltage. Okay, so I hope now you understood that why Q point is required, or what exactly a Q point is. Although I had explained this particular concept in the post of BJT, so if you want to understand this particular concept in much more detailed way, so it's my request to you all guys, please do visit the link which I'm providing in the description section. Okay, so there you will understand this particular concept in great depth. Okay, so let me erase this particular thing. Oh sorry, let me only erase this particular part. Okay, so let's suppose this is the current flowing from drain to source terminal. Okay, and since you are biased this particular MOSFETs, obviously you would be getting one voltage over here, DC voltage VG. Okay, and obviously there would be one voltage across this particular gate source terminal, so VGSQ. Let's suppose not Q. Okay, let's suppose this particular voltage is VGS. So now what we are going to do, we are going to analyze this particular circuit. So this is how this particular part is going to look like. See this particular part, this is how this particular part is going to look like. Okay, so let me move further. Let me take certain different color of pen. Yeah, so this is the voltage VG, and we all know that VG is equivalent to VDD, that means the source voltage VDD into R2 upon just a second, yeah, R2 upon just a second, yeah, R2 upon R1 plus R2. So this is the uh, uh, voltage we would get. Okay, let me just highlight it, and then we will bring it little down. All right, so we'll bring it somewhere over here. Okay, so this is the uh, biasing voltage VG, which is equivalent to VDD into R2 upon R1 plus R2, and this we had got through one formula, or one what I can say, um, theorem, or which is known as voltage divider bias, voltage divider bias, voltage divider bias, or voltage divider technique, or yeah, technique I would write, voltage divider technique. Yes, Now moving further, uh, we all know that to for the MOSFET to work, just a second, I will write over here. For MOSFET to work as an amplifier, right? To work as an amplifier, it should be operated. It should be operated. It should be operated in the saturation region, right? It should be operated in the saturation region. Saturation region. Okay, and the condition uh, for the MOSFET to operate in the saturation region is this. Just a second, let me select some vibrant color. Maybe I will go with this one. Yeah, that means your VDS, it should be greater than VP. Okay, and we all know that VP is nothing but VGS minus of VTH. Just a second, yeah, VGS minus of VTH. That means I'm talking about this particular voltage. Just a second, yes, means see this one over here. So this is your VP, or you can also write it in this way, VGS minus of VTH, right? So this is the voltage I'm talking about. That means this particular region, it is a saturation region. As you can see, this is the saturation region. Okay, I'm erasing all of this stuff because it won't look that good, and I want to include the images in my post. Okay, so I'm erasing this as well. I will just keep VP over here. Yeah, so you're operating this MOSFET, uh, like if you want to operate this particular MOSFET in form of amplifier, so you should always operate in this particular region. Okay, so this is what I wanted to tell to you all guys. But to check whether this particular MOSFET is operating in this particular region or not, so for that we will require VGS and VTH. We all know because this is given by the manufacturer, right? So we need to calculate VGS, and that's why we are calculating over here. We are calculating VGS, plus minus VGS. All right, so we all know that VGS, just a second, let me use certain different color. VGS is equivalent to VG minus of VS, right? So we all know the value of VG. We can easily get that particular value from here. That is not a big deal. Now moving forward with VS, so it would be just a second, let me write it properly. VS would be ID into RS. ID into RS. This is the value for VGS, right? Let me highlight it, and then we will proceed further. So this is the value for VGS, right? And then you will put this value over here, and then you will check VP, right? If your VDS, that means see over here, I will write over here only. There are two conditions, right? If your VDS is greater than VP, then it is operating in saturation region, correct? Saturation, I am writing in short form. Okay, and if your VDS is less than VP, then it may act in the linear region, right? Linear region. Okay, so I hope you know these particular things. Okay, so now we will proceed further. Alright, so with this particular equation, you can check the value for VGS. And now moving forward, so as you can see, this is the outer loop of the MOSFET, and then what we are going to over here is that basically we are going to apply a KVL over here, and then we will see and then we'll find the value for VDS by applying this particular KVL over here. So what I will do, I will write over here applying KVL, applying KVL to the drain source loop or drain source terminal. So we will get the value as plus VDD, just a second, yeah, plus VDD minus ID into RD, right, minus ID, oh sorry, minus VDS, right, and then minus ID into RD, okay, which is equivalent to 0, and thus the value for VDS would be equivalent to VDD minus of ID into RD plus RS. So this is the correct value for VDS, okay, and we all know that value of ID is equivalent to K into VGS minus of VTH the whole square, provided this particular MOSFET is operating in the saturation region. So this is the absolute correct value for the current, okay, and it changes in the linear region, okay, and cutoff it is almost equivalent to 0, where K is half mu n sox W by L, so x W by L, okay. So this is the value for the K, and this particular value you will get with the help of the semiconductors and all in electronic device. You will understand this particular equation, like how this equation how we got this particular equation and all, okay. So as of now I'm not going to deal with this particular parameter, but generally this parameter is known to us, okay, known to us with the help of the data sheet, so you need not to worry about this particular parameter. And what we got from this particular two equation is this. Just a second, let me use certain different color, maybe this one, yeah. See over here, from this two particular equation we will check we'll check the Q point. What we can check is Q point, okay, like where our transistor is operating. If our see over here, if our transistor is operating somewhere over here, okay, we'll try to move this particular Q point at, slightly towards the right side. If our Q point is operating, that means if our transistor is operating in this particular area, so we'll try to move the Q point somewhere over here, okay. And that's why this particular biasing plays a very important role. Why? Because we are making this particular MOSFET or any transistor in general way, we are making this particular transistor to operate in this particular area or in this particular region, so that we can take out the proper amplified form of the signal. And that's the reason that why we prefer using this particular sorry, that's the reason that why we prefer biasing any of the transistor, right? So I hope you understood this particular concept, okay, although I had also explained you this particular thing in my post, okay, but this particular thing needs to be explained in much detailed way, and that's why I had made video on it, okay. So if you have any doubts, feel free to ask me. Thank you for listening patiently. Thank you.